Hey everyone, and welcome back for another deep dive. This time we're taking a look at paradoxes.
Paradoxes, yeah.
Those tricky ideas that seem to contradict themselves, but will still somehow manage to have a grain of truth to them.
Yeah.
We're going to be using a really cool YouTube video as our guide today. It's called Ranking Paradoxes, From Least to Most Paradoxical by ChalkTalk.
Oh, ChalkTalk.
And get this, the rankings are all based on the opinions of 12-year-old students.
Oh, wow.
Yeah.
What a fun way to approach it. You know, they really do highlight those points where our intuition clashes with reason.
Totally.
Paradoxes sort of expose the cracks in our everyday logic.
And who better to point that out than people experiencing the world like with such fresh eyes, you know?
Absolutely.
So in this video, a paradox is defined as anything that basically goes against common opinion.
Right.
But it's got to have a logical argument to back it up. So we're going to be looking at 24 paradoxes today from all different categories. You know, mathematical, philosophical, even scientific ones.
A little bit of everything.
Yeah, it's like a tasting menu for the mind, and you get to decide which ones are most mind-boggling.
Exactly. And the video starts with the paradoxes that the students ranked as least perplexing.
Yeah.
And a lot of those are rooted in probability.
Oh, interesting.
Yeah, things like the birthday paradox,
Uh-huh.
Bertrand's box,
Okay.
and the old classic, the Monty Hall problem.
The birthday paradox always gets me. How many people do you think you need in a room for there to be like a 50-50 chance of two of them sharing a birthday?
Most people, I think, would guess a pretty large number, you know, maybe half the days of the year, something like that. But surprisingly, it's only 23.
Really?
Yeah.
Only 23.
The math just boils down to the fact that as the group size grows, it just becomes more and more probable that any two birthdays are going to match.
Oh, that makes sense. It's amazing how often we're wrong when it comes to probability. And this isn't just some fun party trick or something. I mean, when you really think about it, this principle has some pretty big implications.
Absolutely. And you see this in large data sets, too.
Okay.
Like, imagine you're analyzing customer data. It's actually surprisingly likely to find shared birthdays in there, which could be useful, you know, for things like fraud detection or personalizing those algorithms. Or, you know, think about things like weather forecasting, where they're trying to predict the path of a hurricane. That relies very heavily on these probability models, even things like medical diagnoses.
Oh, wow.
You know, depend on understanding the likelihood of certain conditions.
So maybe not so at least paradoxical after all then.
Right.
So speaking of probability playing tricks on us, Bertrand's box is another one that I find really interesting.
That is a good one.
So we have these three boxes. One has 2 gold coins, one has 2 silver coins, and then the last one has, you know, one of each.
Right.
You pick a box at random,
Yeah.
any box, and you take out a gold coin. What are the chances that the other coin in that box is also gold?
It feels like it should be 50-50.
Right.
But the actual probability is 23.
Oh. Why is it 23?
Well, it's more likely that you initially picked the box with the 2 gold coins in it.
Okay, so why are we more likely to pick the 2 gold coin box?
Well, think about all the different possibilities. There are 3 different ways to get a gold coin. You pick the mixed box and get the gold coin, or you pick the all gold box and get either one of the gold coins.
Okay.
2 of those scenarios involve the all gold box.
Oh.
So it's really about, you know, those different paths to that same outcome.
Right, yeah. Okay, that makes sense. And then, of course, there's the Monty Hall problem with the whole doors and goats in the car thing. That one really messes with my head.
That's a classic.
Yeah.
And the trick with that one is that switching doors after the host reveals a goat actually doubles your chances of winning.
Really?
Yeah, because at first, you only have a 1 in 3 chance of picking the right door. But when a goat is revealed, that probability doesn't just disappear. It actually gets concentrated onto the remaining closed door.
Oh, I see. So it makes me think of like these least paradoxical examples. Do they connect to even bigger questions like the Fermi paradox, for example?
Absolutely. The Fermi paradox it's all about why. With billions of stars and planets out there,
Yeah.
we haven't made any confirmed contact with alien life. Statistically speaking, it seems like there should be other intelligent life out there.
Right.
But the fact that there's no evidence really creates this paradox.
Yeah. And it makes you wonder, like, about what we actually know about the universe and our place in it, you know, and it also emphasizes how our perception of a paradox is shaped by, well, the assumptions that we're bringing to the table.
Totally. And the Fermi paradox, I think, often assumes that intelligent life would eventually develop technology
Yep.
and attempt to make contact with other civilizations. But that might not always be the case. So let's move from aliens to a paradox that hits a little bit closer to home, I think.
Okay.
Have you ever thought about what actually makes a heap? Like, what is a heap?
It's not something you think about every day.
No.
Yeah.
Like, one grain of sand isn't a heap.
Right.
Add another one, it's still not a heap.
Right.
But if you just keep adding, eventually you have a heap. So where's the line?
Yeah. Where do you draw the line? It's true. It's highlighting like that fuzziness of language, I guess,
Yeah.
and how we struggle to define things when it's a gradual change.
Absolutely.
It's hard to pinpoint that exact moment. This kind of reminds me of another paradox called Brace's paradox.
Yeah.
Like the idea that like seemingly insignificant actions
Yeah.
can lead to a much bigger collective outcome.
Exactly. Brace's paradox is a good example of that.
Yeah, that's the one about adding a raid to a network and it actually makes traffic worse.
Yeah.
How does it even work?
So imagine you have two routes connecting, like a city center to the suburbs, and the traffic is evenly distributed. Now add in a new bridge, a third option, that connects these two routes.
Okay, so you think, oh, that's going to help,
Yeah, you'd think it would improve things.
more options.
Exactly. But it often just makes it worse.
Really? Why?
It's because each individual driver is just trying to find the fastest route for themselves, and they all end up overwhelming that new bridge.
Oh,
So you create a bottleneck. If everyone just cooperated and stuck to those original routes, the whole system would be much more efficient.
so more options can sometimes backfire them.
Yeah.
That's so interesting. It really makes you think about how those simple choices can lead to like much bigger consequences.
And this paradox has implications for things like urban planning, even economics.
That's fascinating. It really shows how everything's connected.
Yeah, it really does. Yeah, it really does make you appreciate how interconnected things are. It really does. And that leads us nicely into a set of paradoxes that have puzzled minds for, well, centuries.
Oh, okay.
Zeno's paradoxes.
Oh, yeah, Zeno's paradoxes. I've heard of those.
They use these, like, seemingly logical arguments, but arrive at these really strange conclusions about motion.
Yeah, it's like you think they make sense, but then you're like,
Yeah.
wait,
Exactly.
that can't be right.
Yeah, they're thought experiments, essentially.
Okay.
Yeah.
So like what's an example of one?
Oh, the classic one is the race between Achilles and the tortoise. Achilles, the swift hero.
Right.
He gives the tortoise a head start.
Okay.
But by the time Achilles reaches the tortoise's starting point, the tortoise has moved a little bit further ahead.
Okay.
And when Achilles reaches that new point, the tortoise has inched forward again. And this continues infinitely, with Achilles always closing the gap, but never quite catching up. Ugh. It's like that feeling of always being one step behind no matter what you do.
Right.
But I mean, we all know Achilles would win, right?
Right. But the logic, it seems to suggest otherwise.
So where does the logic break down?
Well, Zeno's paradoxes were designed to kind of challenge the way the ancient Greeks understood infinity and the nature of space and time. They really highlighted those limitations of just pure logical reasoning when you apply it to the actual physical world.
So it's like, our intuition and our real world experience.
Yeah.
We have to use that to inform like our logic.
Absolutely.
It's almost like our brains need like both street smarts and book smarts.
Yeah, that's a great way to put it.
To make sense of the world,
Yeah.
So this whole idea of identity changing over time, it makes me think of another paradox. The ship of Theseus. You heard of that one?
Oh, of course, a classic.
Yeah.
So it poses this question. If you gradually replace all the parts of a ship, is it still the same ship?
Yeah, so imagine Theseus's ship. Over years of sailing and repairs, it has each plank and sail and mast replaced. Eventually, every single piece is new.
Right.
So is it still the original ship or something entirely different?
Yeah, that's a good question. It makes you think about like what actually defines something's identity. Is it just the sum of its parts, or is there something else, something more to it? It even makes you think about like personal identity too.
Yeah.
Like what if we could replace every cell in our bodies?
Right.
Would we still be the same person? It's deep.
Very deep. And it's interesting how the ship of Theseus has found this new life in discussions about AI, artificial intelligence, and consciousness.
Oh.
Like if we create an AI and keep updating its code,
Right.
At what point does it become a different entity?
Yeah, that's a really good question. Okay, well let's move on to a paradox that tackles ultimate power,
Hmm.
the omnipotence paradox.
Okay, so the omnipotence paradox asks, can an all-powerful being create a stone so heavy that even it can't lift? Oh, so if it's all-powerful, it should be able to create anything.
Right, right.
But if it's all-powerful, it should also be able to lift anything, right?
So the very definition of omnipotence just creates this contradiction.
Exactly. It really makes you think about those limits of logic and language when you try to describe these concepts that are just so beyond human experience.
Yeah, yeah, I get that. Okay, so let's switch gears a bit and talk about like paradoxes that aren't quite as, well, paradoxical once you kind of understand them.
Right. The ones that start out confusing, but then, once you have a bit of an explanation, it's like, oh,
Okay.
I see.
Yeah, yeah, some people find those a bit frustrating.
Right. Even annoying sometimes.
I get that, yeah.
So, for example, we have the potato paradox,
Okay.
which is just this word problem that, when you try to do it with simple algebra, it leads to this impossible answer.
Okay.
And then there's the infamous 1 equals 0.99999 and so on.
Yeah, some people, they just refuse to believe that.
I know. It looks like a contradiction, but with a little bit of mathematical understanding, it becomes clear that they actually represent the exact same value.
Oh, okay, I see. So it's a good reminder that what seems paradoxical at first
Heh.
might just be a gap in our understanding.
Yeah.
Okay, well, now I'm ready for something truly mind-boggling.
All right, so prepare yourself for Gabriel's wedding cake.
Gabriel's wedding cake. Okay, what's that one?
So imagine an infinitely tall wedding cake.
Wait.
Each layer is a meter high, but the radius of each layer, it gets progressively smaller. 1 meter, then a half a meter, then a third, and so on.
Okay, so it's like this infinitely tall, but like increasingly narrow cake. So does that mean it has an infinite volume?
You would think so, but using calculus, we can actually calculate that it has a finite volume.
Wait, so an infinitely tall cake could actually fit in like a normal-sized bakery?
Yeah.
That's incredible.
It's amazing, right?
Yeah.
So it really just shows how, in math, these infinite series can lead to these very surprising and counterintuitive results.
Yeah.
And speaking of infinite series and counterintuitive results,
Okay.
let's talk about super tasks.
Oh, yes.
You like those?
I love a good super task.
Yeah.
Give me all the mind-bending scenarios you got.
Okay, well, first up is the alternating sum paradox.
Okay.
Imagine you're adding and subtracting 1 an infinite number of times. 1 minus 1 plus 1 minus 1 plus 1 and so on forever.
Okay. So is the answer 0, 1, or something else completely?
That's the paradox.
Oh.
Depending on how you group the numbers, you can actually get different answers. And in modern mathematics, this is actually considered a divergent series, meaning it doesn't have a single defined sum.
Oh, okay. That's really messing with my sense of order.
I know, right?
What other super task paradoxes do we have?
Okay, so the next one is Thomson's lamp. So picture a lamp that's switched on and off infinitely many times, and each time you flip it, you have the time between flips.
Okay.
So at the end of this super task, is the lamp on or off?
Oh, that's a tough one.
Yeah.
It can't be both. Right.
Yeah.
I'm going to go with Erd, but I have no idea. What's the answer?
There actually isn't one.
Oh.
The lamp state in that final moment is completely undefined.
Oh.
It just shows how our understanding of these finite processes doesn't really work when we start dealing with infinity.
Okay, so infinity just equals undefined, basically.
Pretty much. And then we have the Ross-Littlewood paradox, which is all about adding and removing balls from a vase
Okay.
an infinite number of times.
Yeah.
It leads to some very strange questions about how many balls are left at the end.
Okay, so that one sounds like a rabbit hole I might have to go down later.
Yes, we'll be sure to include some links in the show notes for anyone who wants to learn more about that one.
Perfect. Okay, so moving away from infinity for a sec.
Uh-huh.
Let's look at a paradox that combines probability with like real-world decision-making.
No.
The St. Petersburg paradox.
Yeah, so this paradox is all about a casino game with the potential for winning an infinite amount of money.
Okay, I'm intrigued.
Yeah. So imagine a coin flip game where you win $2 if the first flip is heads, $4 if it takes 2 flips to get heads, $8 if it takes 3 flips, and so on.
Okay, so
Wow.
the potential winnings just keep doubling.
Exactly.
Wow. So theoretically, you could win like an astronomical amount of money.
Yeah, and that's where the paradox comes in.
So what's the paradox, though?
Well, if you try to calculate the expected value of this game, it's actually infinite.
Okay.
But but realistically, would anyone ever pay an infinite amount to play? Of course not.
Right, of course not.
And most people wouldn't even pay, a very large amount to play because the odds of winning those really big sums are so slim.
Right. Yeah, that makes sense. So this paradox is really showing that like there's a difference between that theoretical probability, like what the math says,
Yeah.
versus like actual human behavior.
Exactly. It shows that we're not always completely rational when it comes to risk and reward, even if the math is, perfectly clear cut.
That's interesting.
So the St. Petersburg paradox, it gives us a glimpse into how our brains actually work when we're faced with uncertainty.
Okay, yeah. All right, well, buckle up, everyone, because it's time to enter the realm of self-referential paradoxes. These are the ones that will really twist your brain into knots.
Yeah, they really do. They're like those linguistic black holes.
Oh, okay.
They just kind of collapse in on themselves, creating these inescapable loops of logic. It's like language trying to bite its own tail.
Ooh, I like that. So what's like a classic example of this?
Well, one of the most famous ones is the Berry paradox.
Okay. The Berry paradox.
Yeah, so it asks you to consider the smallest positive integer not definable in under 60 letters.
Okay, so there's a lot of numbers we can define in under 60 letters, obviously.
Yeah.
I mean, 1, 17, 4,002.
Right.
You get the idea.
Yeah, but because, our alphabet's limited, there's only a certain number of phrases that we can make with 60 letters or less.
Right, a finite number.
Exactly. And since there are infinitely many positive integers, there has to be some that we just can't describe with that few letters.
Yeah, I mean, there's too many numbers.
Right.
Not enough, like, short phrases.
Exactly. So far, so good, right?
Yeah, okay. But this is a paradox, so.
Right. This is where it gets interesting. So if there are numbers we can't define in under 60 letters, there must be a smallest one among them, right?
Okay, yeah, that makes sense. So let's call it x.
Okay, so x is the smallest positive integer not definable in under 60 letters. But wait a minute.
That definition is under 60 letters.
Exactly. We just define the undefinable.
Oh, wow.
So the Berry paradox creates this self-contradictory loop where the definition just undermines itself.
Right.
And it just shows how slippery language can be and the limitations of trying to pin down these concepts, with these finite systems.
Yeah, my brain feels like it's doing somersaults right now. That's incredible. And there's also the Grelling-Nelson paradox, which plays with this idea of words that can describe themselves.
Right. And we call those words autological.
Yeah.
Like the word short is short. The word English is an English word. You get the idea.
Yeah.
And then you have words that don't describe themselves, and those are heterological.
Okay, so like long is not a long word.
Exactly. Or monosyllabic is not a monosyllabic word.
Right.
But now think about the word heterological itself.
Okay.
If it's heterological, meaning it doesn't describe itself,
Yeah.
then it must actually be autological because it would describe itself as not describing itself.
Oh.
But if it's autological, meaning it does describe itself,
Yeah.
then it must be heterological. It's just this never-ending loop.
So is heterological autological or heterological? It's like I'm trapped in some kind of linguistic hall of mirrors.
I know, it's a fun one to think about.
Okay, well, these self-referential paradoxes are wild.
They are. And it's not just language that can create these mind-bending illusions. We also have visual paradoxes, too, that play with our perception.
Oh, okay. So, like, what kind of visual paradoxes?
Well, think about the work of M.C. Escher, for instance.
Oh, yeah. Those impossible staircases, the buildings that just defy the laws of physics.
Yeah.
Those are so fun to look at.
Right. And one of his famous pieces, Ascending and Descending, it depicts this never-ending staircase, and these monks, they're always climbing, but they never actually get any higher or lower.
Oh, right.
So it creates this disconnect between what we see and what we know to be true.
Yeah. It's like our brains just can't reconcile it. Like they're trying to make sense of something impossible.
Right.
And then there's like the classic Miller-Lyer illusion with the two lines. Like they're the same lengths, but they look different because of the arrows at the ends.
These visual paradoxes, they really show how our perception is shaped by all these things.
Yeah.
Context, our past experiences, even, cultural biases. It makes you wonder what's actually objective reality,
It's a good reminder that seeing isn't always believing. Okay, are you ready to tackle the top 3 paradoxes from the video?
Yes, let's do it.
The ones that the 12-year-olds found the most mind-boggling.
Okay, so number 3 on the list is the pop quiz paradox, which I'm sure we can all relate to.
Oh, yeah, that one always makes me think of school. Okay, so remind us how this one works.
So imagine your teacher says there's going to be a surprise pop quiz sometime next week.
Okay.
But you start thinking, it can't be on Friday because by Thursday I would know it was coming.
Right.
So you eliminate Friday, but then it can't be on Thursday either because by Wednesday afternoon you'd know it was Thursday. And so this reasoning just continues until you've ruled out every single day of the week.
So logically, there can't be a pop quiz at all. But then,
But then your teacher gives you a pop quiz anyway, so it just exposes that flaw in our backward reasoning and reminds us that we can't always predict the future based on just eliminating possibilities.
right, sometimes the unexpected just happens, and we have to adapt. Okay, so what about number 2 on the list?
Number 2 is Simpson's paradox,
Okay. Simpson's paradox.
which shows how trends can actually appear to reverse when data is aggregated differently.
Okay, so give us an example of how that works.
Sure. So imagine you have two baseball players, player A and player B. Player A has a higher batting average than player B in both 1995 and 1996. But when you combine the data from both of those years, player B actually has the higher overall average.
Wait, how's that possible? How can you have a lower average each year, but a higher overall average? I feel like I'm in the twilight zone.
So it's all about the number of at-bats that each player had in those years. So imagine player A had like a stellar year in 1995 with a very high average but very few at-bats.
Okay.
Then in 1996, they had a lot more at-bats but a slightly lower average, and player B could have had like a slightly lower average both years but consistently more at-bats, leading to a higher average overall when you combine the data.
Oh, that's a really good explanation. So it just shows how important it is to consider like all of the variables, and not jump to conclusions based on just these simple trends.
Yeah, and Simpson's paradox has implications for a ton of different fields, medical studies, social science research, and it really just underscores the importance of careful data analysis and being aware of the limitations of statistical interpretations.
Right. The moment we've all been waiting for, the number one paradox, the one that just blew the minds of those 12-year-old students.
Right.
What is it?
It's the liar's paradox. It's a classic for a reason, and it's the simple statement, this sentence is false.
Okay, that sounds simple enough, but I have a feeling it's not.
No, it's not, because if the sentence is true, then it must be false.
Oh, right.
But if it's false, then it must be true. So it's just this endless loop.
It's like a logical Ouroboros.
Yes, exactly. It just keeps devouring its own tail. And the liar's paradox has puzzled philosophers and logicians for centuries because it really challenges like our basic assumptions about truth, and self-reference and just the limits of language.
This deep dive has been an incredible journey. We've gone from like probability puzzles to infinite cakes, from self-contradictory statements to impossible staircases. These paradoxes have really stretched our minds and made us question everything we thought we knew about the nature of logic, language, even reality itself.
It has been a wild ride. And remember, everyone, this journey doesn't end here. Keep questioning, keep exploring, and keep your minds open to the possibility that sometimes those most baffling contradictions, they can actually lead to some pretty profound insights.
Well said. Thanks for joining us on this deep dive into the paradoxical. Until next time, keep those paradox detectors on high alert. And remember, sometimes the most confusing ideas can also be the most illuminating.